Hello everyone. In this video, we will talk about block diagram and system realization. Basically, you have a system described by the transfer function. This could be a simple system or complex system. A system that will take a speech signal and filter out noise like a tone, or as complex as your telephone that analyze your signal, sample it, then transmit it. Or it could be like an ECG system that pick up the electric field from the heart muscles and process it and show the nice ECG. So we will discuss, for example, this simple system, which is a bandpass filter. How do we build this system in real life and start using it? This is the topic of today's lecture. So we're gonna cover the following: Form 1 realization and Form 2 realization and the transpose realization. And then how do we break a very complex system to a simpler subsystems, either connected in cascade or in parallel realization. Then we will talk about the finite impulse response system realization. And these systems will consist of the following: a summing amplifier, inverting op-amp or non-inverting op-amp, and a delay and a memory component. So no matter how complex is the digital system, it basically consists of these basic components: amplification, summing, memory, or a delay. All right, before we start, let's talk about basic connection that we will be using. First, the parallel connection. So if you have two subsystems connected in parallel, and I want to represent it as one system, the output of this subsystem will be H1Z X of Z. The output of this subsystem will be, now here I am summing both of them. So this output will be this one plus this one, and it will be, now I can take X of Z as a common factor, and this will be, so to represent this as one system, it will be H1 of Z plus H2 of Z. Now cascade connection, you can think of it as follow. The output here, W of Z, will be, now this input will go to this subsystem. So this output then will be the input times the transfer function of this subsystem. So now I can think of it as this is one system. So when you have two subsystems connected in cascade, their total transfer function is just the multiplication, H1 of Z times H2 of Z. Now the feedback system is an important one. Now if I want to find what is the total transfer function of these two subsystems that are connected as feedback. So E of Z here consists of the following: X of Z added to it this signal here, which is H of Z times Y of Z. So the signal at this node is just H of Z times Y of Z. So then, and this is the negative, so this would be negative. Okay, so now the signal at this node will be this input E of Z times G of Z. Let's clean up. Now I need one equation that has only X of Z and Y of Z. So I can find what is the total transfer function of this feedback system. So I can replace E of Z here by its value here. And let's multiply. And let's bring this term to the left side of the equal sign so I can gather all Y of Z. So then this will be, now to find H of Z, I need to have Y of Z divided by X of Z. So I can take this as a common factor. Okay, the last step, divide Y of Z by X of Z. So I'm going to divide this by X of Z. and divide this by this component. So h of z will be which is this one. I want you to remember the following. This is positive because in the system it's a negative feedback, so this is a negative sign. So when we do system realization form 1 and 2, keep this in your mind. Now, feedback is extremely important. If you design any system without a feedback, it's vulnerable to collapse, to fail. It might work perfectly for certain input and it's faster and use less resources, but you cannot guarantee that one time or one day this input will be corrupted by noise and the system will not be able to handle it, and eventually either it will collapse or give you ridiculous output that may damage all subsystems connected after it. Yes, feedback slow the system. Yes, feedback create more complex processing, more expensive system, but it will work for a long time and will give you good data. And just imagine the human body. Every subsystem in our body has a feedback, the eyes. If you go from a dark room to a bright room, there is a feedback that the brain will send action potential to make the pupil narrow. So less light will go in to protect the retina. Same thing our auditory systems. There are muscles connected to the stapes. If you are going from quiet room to a very loud room, within a minute you start feeling you are not hearing it as loud as it used to be, because the brain's feedback send action potential to the muscles to make the stapes stiff. So feedback is very important, and we will see it in system realization. So any system, no matter how complex it is, it can be described by a transfer function like this one. This system is of k order. K could be a 10th order, 12th order. The higher the number, the more complex the system. And usually if the system is causal, k will always be equal or larger than L. Now, if I want to build this system, I need it to be a delay. So that means every z you see in the numerator and denominator should be to the power of negative value. So we know that h of z equals z minus 1 is a delay system. Let's prove that. This is just basically y of z over x of z. Now this is y of z. Now if I do the inverse z transform, this is just y of n. So this is basically a delay system. The output, just the input delayed 1 unit. Okay, to make z in the numerator and denominator to be to the power of a negative number, then I will multiply numerator and denominator by z minus k, because k is the largest possible number. This will make every z in the numerator and denominator to be z to a negative power. So for example, this will be z to the power of L minus k. L could be 5, k could be 7. So that would be z to the power of negative 2. So you will get this equation. Here, when you multiply it by z minus k, you get 1. Now, by doing this, z will always to be negative 1, negative 2, negative 3. So that's a delay system. Now, I will break this equation to be two subsystems connected in cascade. So one possibility is you take the numerator to be your first subsystem, which is here, h1 of z. Then you take 1 over the denominator, and that will be your second subsystem connected in cascade. If you multiply these times this, you will get back this system. If I order them this way, h1 of z here and h2 of z, so h1 is the numerator, h2 is 1 over the denominator, then this will be direct form 1 realization. If I switch the order between these two, so this will be the first subsystem and this will be the second, then this is direct form 2 realization. So let's take an example and see how we will get the direct Form 1 realization. So I have this second order system and I want to realize it using Form 1 realization. So I will divide numerator and denominator by z squared. So this will be, when you multiply by z minus 2, this will be same thing. I can divide this by z squared or multiply it by z minus 2. So this will be, now Form 1 realization, this will be the first subsystem cascaded with 1 over the denominator as the second subsystem. Now this subsystem looks like a feedback, exactly like this one, where g of z in this case is just the 1, h of z here is this one, and that one here is this. Now let's write h of z as y of z divided by x of z. And let's do the following. Y of z equal. Now x of z is the input to this subsystem. Now let's draw this. First we're gonna create the node x of z. Now the input go to an amplifier, so that will be B0. The arrow is like an amplifier. Also the input is going to a delay and then amplification of B1 and amplification of B1. Also the input is going to a second delay and amplification of B2. So this is the first delay, second delay, and then amplified by B2. Now I add all these branches, plus plus. So I will put a summing amplifier here and connect this one here, and I have a summing amplifier here and connected here. Now at this node, let's call the signal, which is x of z going to here, w of z. So this is w of z. Now w of z is going to this feedback. G of z is 1, which is this one here. This is g of z. This is here 1. So that will be 1. Then it goes to this feedback, and that will be h of z, which is here. You can think of this as h of z multiplied by 1. Now I will draw this subsystem, which is this. Y of z will go through a delay and amplified by A1. Then it go to a second delay and amplified by A2. And this is a summing amplifier, and it goes here to a summing amplifier. Now when we derived the feedback equation here for this feedback system, the sign here was a negative. So in order to make the summing amplifier like inverting op-amp, I can put a negative here and that will be fine. Or if this is just a regular summing amplifier, then I can put the negative here and here. And this will be just positive like all others summing amplifier. And this is Form 1 realization. Now, in practice, Form 1 realization is very easy to go from the equation to the system, and even to go from this plot to the difference equation. For example, y of z here will be y of n is equal. Well, the signal here is y of n is delayed 1 unit, then amplified by minus a1. So it's equal minus a1 times y of n minus 1. And then y of n here, it's delayed once here, then it's delayed second time here and multiplied by minus a2. So that will be minus a2 y of n minus 2. And they are added here. And they are also added to w of z. And w of z consists of what? Consists of x of z multiplied by b0. So that's plus b0 x of n. Also, w of z, this added to it, which is the flow here. That will be x of n delayed 1 unit multiplied by b1. Plus this signal coming through here, which is, so from Form 1 realization, very simple to go to the difference equation. The only drawback of Form 1 realization, it uses many delays and memory. So let's move on to the Form 2 realization, which is more common. Let's clean up. Now in Form 2 realization, 1 over the denominator will be our first subsystem. Then the numerator will be our second subsystem. So let's build this subsystem first. So let's draw the node for the input. Let's clean this. Now g of z here and here is 1. So that is 1. All this here is h of z, which is this one. So now this node here, you can think of it is this node. Now the signal here, which is here, will go to this subsystem, which is a delay first, then amplification by A1, which is minus A1. Then it go to a second delay and amplification by A2, which is negative feedback, so that's negative A2. And then I sum them up. And then it goes to here. I don't have a negative here because I already put it here. Now, the output of this subsystem will go to this subsystem. So that is pure amplification by B0. And then a delay and amplification by B1. So then that's a delay. So that's here, a delay and amplification by B1. Then it also to go to a second delay, so that's a second delay, and amplification by B2. Then I sum all of them here. And this is y of z. And this is Form 2 realization. Now, if I compare Form 2 realization and Form 1 realization, we will notice the following. Form 2 realization only use 2 delay. Form 1 realization use 4 of them. So that's why Form 2 realization is more common. It uses less component, it will be faster, and the smaller the system, the less possibility for error. And Form 2 realization, they also call it the Canonic Form realization. Okay, the next one is transpose realization. We can get the transpose realization from Form 2 realization by doing the following. First, you switch the direction of the arrow. So this will be here, this will be here, this will be here, and this one will be here, and this one will be here. Convert the node to a summing amplifier, and a summing amplifier converted to a node. And this is a summing amplifier. And call this y of z, and call this x of z, and then do 180-degree rotation. So this side will comes here, and this side will comes here. Or actually, you can find the transpose realization directly if you make the numerator of the equation the first subsystem, just like Form 1 realization, and 1 over the denominator as the second subsystem. And instead of delay then amplify, no, do amplification then delay. So let's follow this technique. So we draw the node for x of z, the input. So I will do amplification first, then delay. You can think of this h of z as y of z, and then here x of z. So x of z is going to this subsystem. So that will be amplification first. Then it's going to this, which is amplification and the delay. So I will do the amplification first, then the delay. And now I have to sum these two components. And x of z also going to a second delay and amplified by B2. So I take x of z from here amplify by B2, and then it go to a delay here. Then this will be the second delay. But since these two signals coming here, I need a summing amplifier here. Now, X of Z times this will give you W of Z. You can think of this here is W of Z at this node. Now, W of Z will go to this feedback. So W of Z will go to this feedback, which is amplify first, then delay. So that will be, it's like going this way. Then it's going to amplification of A2. So that is minus A2 and a second delay. So that's going to be the first delay, and this will be the second delay. But then it's connected to this signal, so I need a summing amplifier to add them up and control the direction to be this way. So summing amplifier, you need it because it will add two signals and you want to direct it in this direction. And this is the transpose realization. It's as efficient as Form II realization. Let's take examples. We have this second order system and we want to realize it using Form II realization and the transpose realization. So the first step is that 4 I need it to be 1 and Z square I need it to be 1. So I will divide every element here in the numerator and denominator by 4 to make this 1 and multiply by Z minus 2 to make this 1. So H of Z will be 2 divided by 4, that's half, multiplied by Z minus 2, that is Z minus 1, minus 3 over 4 Z minus 2. And here it will be 1 minus 1 over 4 Z minus 2. Form II realization is the feedback first, so 1 over the denominator times the numerator. Let's draw the node for the input. So it will go to 2 delay and the second one and amplified by minus 1/4 and sum it here. So let's just move X of Z here. Now X of Z already went to this subsystem, so the output of this subsystem, let's call it W of Z. So that will be here. So W of Z will go to a delay and amplification by half. So W of Z here will go to a delay and amplification by half. Also W of Z will go to a second delay. So W of Z here, go first delay, second delay, and amplified by minus 3 over 4. Then I sum these components here. And that's Y of Z. And minus times minus, that's just positive. Now to do the transpose, I will express it as first the numerator, then 1 over the denominator. So let's draw the node for the input. So you can think of this like Y of Z, and then we bring X of Z here. So X of Z is going to amplification by half, and then delay. Also X of Z is going to amplification by minus 3 over 4, and delay. Delay twice, so this will be the first delay here, and going here through the second delay. And X of Z going to this will give you W of Z, which is this node here. Now W of Z will go to this feedback. G of Z is 1, so that's 1. Then it go to this feedback, which is a delay twice, so then I'll draw 1 here, and amplification by minus 4th, since it's a negative feedback, this minus 4th, and I will need a summing amplifier here to direct the flow of the current or data, and that will be here is Y of Z. the output. And this is just positive. Next is cascade and parallel realization. Here you may have a very large system, something like this. This is not even large, it's fifth order automobile suspension system. Now, if I want to program a DSP board to perform the operation of this system, could be also electronic system, I will need a long word. That means the number of bits to represent this number accurately. It may be 12, 16, even 28 bits, or this one, or 64 bits. And any deviation from these numbers, the performance of the system will change. It will not be as the criteria we use to design it. So one solution to this problem is to break this large system to many subsystems, smaller order, second order, first order, and connect them either in cascade or in parallel. These numbers will become very small and can be represented by 8 bits. Let's take this example. This is a system of second order, and I want to represent it as a subsystem of first order, either connected in cascade or connected in parallel. So the first step is to factor out the denominator in this form. Now, if I want to connect this system as two subsystems in cascade, I can do the following. I can consider this as one subsystem, and this will be this one. And consider this as my second subsystem, and this will be this one. And I call this H1 of Z, and this one is H2 of Z, and they are connected in cascade. If I multiply these two terms, I will get back the original signal or system. So let's see how we're going to build this subsystem. Let's clean up first. So first we're going to build H1 of Z. And we will be using Form II realization. So I will divide everything by Z or multiply by Z minus 1. And I can do the following as Form II realization: 1 over the denominator, my first subsystem. My second subsystem will be the numerator. Now let's build this subsystem. So this is the node for the input. It go to this feedback, which is a delay. Then amplification by minus half. And that's a summing amplifier. Now the output of this subsystem, W of Z, which is this node, will go to this subsystem, which is a delay. So it will go back here, delay, and then amplification by half. And let's call this node the output of this first subsystem. And this will be H1 of Z. Same thing, let's build this subsystem. H2 of Z, let's do it here. Multiply by Z minus 1. 1 over the denominator, our first subsystem. Now, to build this, let's draw the node for the input for this subsystem. It go to a feedback, which is a delay amplified by, or a multiplier by minus half, which is plus half. Then go to a summing amplifier. Then let's call the output of this one is V of Z. So that will be the node here. Now the output will go to the subsystem, which is a gain of 1. So that's a gain of 1. And also will go to a delay and amplification by minus 3 over 2. So it will go here and back here and gain of minus 3 over 2. And then you sum them up. You sum these and these. and we will call this the output of the second subsystem. Now the input to this subsystem is the output of this subsystem. That means the input to this subsystem here is the output of the first subsystem. So I take a piece of wire and I connect it. And that's the two subsystem in Cascade, and this will be y of z. Now, if I want to build this system as two subsystems connected in parallel, then from this point here, I have to do partial fraction expansion, which will be a over z plus half plus b over z minus half. And if you solve this problem to evaluate a and b, you will get this one. A will be 1 and b will be minus half. Now I have these two subsystems connected in parallel. And if I call this subsystem here h3 of z, let's build it. So I multiply numerator and denominator by z minus 1. So I get here z minus 1. Again, just a reminder why we multiply by z minus 1, because we want the system consists of a delay element. That's one reason. And the second reason, I can create a feedback. So these can be consist of two subsystems. One is a feedback, one is forward subsystem. The feedback will be 1 over the denominator. And the second subsystem will be the numerator. Now, if I build this, let's say this is the node of the input, and it's going to a delay and gain by minus half, and then a summing amplifier here. Then the output of this one will go to a delay. So to go back again to a delay and gain of 1. So this is the output of h3 of z. Now let's build h4 of z, and let's do it here. Again, multiply by z minus 1. And if I build this subsystem, now let's clean here first. If you think of h of z as y of z divided by x of z, then I can bring x of z here, and also because of this plus sign, it should be also multiplied by this term. So now you have here x of z, and also here x of z. So the node to this subsystem will also be x of z. So I can connect a piece of wire here, and then I call this x of z. Now this input will go to this subsystem, which is a delay, and amplified by minus 1. So minus times minus, that's plus 1. The summation. Then the output of this subsystem will go to this one, which is a delay and amplification by minus half. So that would go back here, and minus half. And the output of this subsystem and this one, they are added by this plus sign. So I have a summing amplifier here, and they add these two. And that's the output. Let's clean up. Now we have the same system represented in Cascade this way, which is this one, and represented in parallel, which is this one. If you have the choice to connect them in parallel or in Cascade, it's better to connect them in parallel for the following reasons. One, first, in parallel, this subsystem here and these start processing the input at the same time. So it's usually in parallel realization is faster. The second advantage is if something went wrong in this subsystem, it will not affect this subsystem. So the error will not propagate. But in Cascade, if error happened in this subsystem, that error will propagate to the second subsystem. And the probability that the error will be even worse is much higher than canceling. So parallel realization has an advantage over Cascade realization, But certain processing, you have no choice other than Cascade. Basically, you need the input to be processed first by this subsystem, then the outcome of this goes to the next one. Okay, let's clean up. Now, what if you have a system and you want to break it to a smaller subsystem? And when you did the factoring of the numerator, you end up with this conjugate. Now, this conjugate, you cannot really build or program your DSP to carry this operation. So go back again and combine these two terms. So it will be the second order subsystem. You cannot make it any simpler. So this one will be then this and this one. Now everything here, these numbers, parameters are real. So you can program your DSP to carry this operation. And the same thing, I can express this in parallel and it will be this one. Now, there are different ways of realizing the same equations, but one realization will be more efficient than others. As an engineer, you have to be very efficient in building systems. The more efficient is the system, the longer it will survive errors, noise, and better performance. For example, if I have this large system and I want to break it as subsystem. So one way is this one. So it will consist of 3 subsystems. Now building this one is here. This will be this subsystem. And building this one in parallel, it will be this subsystem. Now without thinking, I can build this subsystem here in parallel too. And this will be here. And the input will come here. But then this one will have actually 2 delay because it's z squared. Since these two are repeated roots, so I can do the following. To build these, I will make it 5 over z minus half. And I will connect these in cascade with these. So if I multiply these two terms here, since they are connected in cascade, I will get this subsystem. So this subsystem will be this one here, connected in cascade. And then all 3, 1, 2, 3, connected by the summing amplifier. So this is more efficient than building the second order. So I end up making this one just a first order, but cascaded with this subsystem. Now the last topic in this video is realization of FIR filter, finite impulse response filter. FIR filter, usually the output y of n depends only on the input, the current input, and previous versions of the input, or the inputs 1 unit earlier, like this one, and this is 2 units earlier, and this is k units earlier. In FIR, the output will not depend on previous output, like yn minus 1 and so forth. If you have this term, then this would be IIR, infinite impulse response filter. Okay, so how do we build FIR system? Let's take this example. This is an FIR system. So to build this subsystem, let's find the Z transform. So if you do the Z transform, half now if I take x of z as a common factor and take it under y of z, then I will get this one. Now this is the transfer function, h of z of the system. So to build it, it will be this input going to all these components. So let's draw the node for the input, that's x of z. So x of z is multiplied by half, that's the half. And plus x of z is delayed 1 unit and multiplied by 1/4. Plus x of z is delayed 2 unit and multiplied by 1/8. So that's x of z 1 unit delay, another one. And x of z is delayed 3 units and multiply by 1/16. So again, x of z here, delayed 1, second, and third. And multiply by 1/16. And now I add them up. So this will be added to here. And that's the output. Now, if I want to build this subsystem in a transpose realization, then I do first the multiplication, then the delay. So I start with the input x of z. So first we start with the multiplication, then the delay. So we usually will start with the last one, the most delayed one. So then this will be the multiplication 1/16, and it's delayed 3 units. That's 1 unit, second unit, 3 unit, and that's the output. Plus, then we start with this one, delayed 2 unit and amplified by 1/8. So x of z delayed 2 units and multiply by 1/8. That's the 1/8, and this is the 2 units. Now here you cannot just put a node, because you want that current here or the signal here go this way, not go this way. So I add a summing amplifier here between these two nodes, so it will direct the signal to flow in this direction. Then building this one, it's a delayed 1 unit and amplified by 1/4. So that's the delay 1 unit and amplified by 1/4. Again, I cannot have a node. I have to have a summing amplifier, so it will add this signal here and this signal here and direct it to go here. Plus x of n amplified by half. So that's x of n amplified by half. And I have a summing amplifier, and that's y of z. So this is Form II realization. This is the transpose realization. Here it's delay, then amplification. Here it's amplification, then delay, amplification, delay, amplification, delay. Let's clean up. I can even express this as 2 subsystems connected in Cascade. So the first step is you multiply everything by z cube, z to the highest negative, so you will get this signal. Then you factor out the numerator, so it will be this time this, and the z cube you can distribute it this way, or you bring the z square here and the z here, it doesn't matter. And now you build this subsystem first, then you build this subsystem second. This will be first order, so that will be this one. And this subsystem here will be a second order, and that will be this one. And they are connected in Cascade. As I said before, Form II realization and transpose is better than Form I realization. It uses less delay element. But breaking a large system to a smaller subsystems and connect them in parallel or in cascade will eliminate the finite word length errors. When you have z squared plus az plus b, those, if they are a large number, they will need large number of bits. If you break it to a subsystems, then these numbers will become smaller, and the finite word length error means instead of having 0, 1, 1, 0, 0, 1, 1, 64 bits to represent this constant, you will need only 16 bits. So you minimize the finite word length errors. Parallel realization is better than Cascade if you can do it, because it minimizes error propagation and it's faster processing. All right, this ends the lecture in this video. Thank you for watching, and see you next video. In frequency response and discrete time system design.